Hi everyone, this is the third and final video for section 9.3. It's also the last video of the semester, woohoo. So this last video is going to talk about some famous irrational numbers. So these are the things that I referenced up here when we talked about irrational numbers. So square root of 2, pi, e, and phi, however you want to say it, it's the Greek letter. So we've already talked about square root of 2. You should have at least gone back and read the proof on page 349 that square root of 2 is irrational. So now we're going to talk about these other three, which are pi, e, and phi. Okay. So the first one, pi. So pi is defined as the ratio of the circumference of a circle to its diameter. So it's always going to be this fraction, circumference over diameter. And so for any circle, this ratio is going to be the same. And so that's what made people first interested in pi, is that they noticed that if we had a circle with a diameter of 1, then the circumference was going to be 3.14-ish. And if the diameter was 2, then the circumference was going to be 3.28-ish. So around 3.14 for a diameter of 1, and around 6.28 for diameter of 2. And so they noticed that this was always the ratio was 3.14, around 3.14. And so this ratio is represented by the Greek letter pi. And so this is one of the most common irrational numbers that we talk about. So it has a lot of different approximations. And so one of them is 3.14. That's the most common one. 22 over 7 is a really common fractional approximation. And then 355 over 113 is a less common fractional approximation. But it's roughly 3.14159. And this is an irrational number. It is not a terminating decimal, which means it goes on forever. And it's also not repeating. So there's no pattern in the decimals of pi. So this is something that's been studied a lot, just because it is infinite. And there's a lot of competitions. I know I talked about math competitions in one of the other videos of chapter 9. And there's math competitions of how to see how many digits of pi people can memorize. And it's a lot. People can memorize a lot of digits of pi. So you'll use this if you ever teach geometry. This is where it starts to be involved, is anytime you start talking about the area of circles, the circumference of circles, things of that nature. But one thing to note is that 3.14, 3.1429, and 3.14159 are only approximations of pi. They're not equivalent. So these aren't the same. These are approximations. So you'll have noticed by now on your on your WebAssign homework, that if you round decimals, they don't like that, especially if you have something that isn't a terminating decimal. So they really don't like when you round repeating decimals. It's the same thing. These are really close, but they're not the same. So you shouldn't treat them as the same thing. These are approximations. And you can see that whenever you look at these approximately equal to signs, these little squiggly equals, this means approximately equal. And so pi is approximately equal to all of these things, but not exactly. And you can see how to use pi to solve a problem on page 351. It's just setting up a proportion. If you're given the circumference or diameter of a circle, then you can find the other one setting the circumference over the diameter equal to pi. And you can solve problems that way. Okay, the next number we're going to talk about is Euler's number. So Euler was a famous mathematician who came up with a lot of things. And one of these things that he came up with was this definition of E. So E, just the normal English letter E. So it's this infinite sum where you keep on going forever. This should have a plus ... And so it's just 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4, and so on. So if you do this infinite sum, you can approximate E. So E is approximately equal to 1.71828,183. So what it's actually equal to is what I wrote in the first video, 2.71828,1828, and the 1828 just keeps repeating forever. So this isn't a repeating decimal though, because of this 7 right here. So because this 7 isn't part of the repeating part, this is not a repeating decimal. And so that is what makes it irrational. So it's used a lot in continuous compound interest, exponential growth or decay, and logarithms, things of that nature. So this has a lot of applications. Yeah, one of the most common is finding interest. For the example 5 in the book talks about using the formula A equals PE to the RT to find interest. So you can look at that there. And the last number we're going to talk about is phi. So phi represents the golden ratio. So we have looked at the Fibonacci sequence before. And so the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, right? Remember that in order to get this 2 here, we added the 1s in front of it. In order to get the 3, we add the 1 and the 2 in front of it. The 5 is the sum of the 2 and the 3 in front of it. The 8 is the sum of the 3 and the 5 in front of it, and so on. So to get the next term, you would add the 2 terms before it. And so we can look at the ratio of the consecutive terms. So if we look at the first 2 terms, we get this 1/1. If we look at the second 2 terms, we get this 2/1. And then the next 2 is 2/3. Sorry, 2 and 3 gives us 3/2. 3 and 5 gives us 5/3. 5 and 8 gives us 8/5. 8 and 13 gives us 13/8, and so on. So we can look at the ratio of all of these consecutive terms. And whenever we expand these into decimals, right, whenever we do the implied division that's in every fraction, we get these ratios. So 1/1 is 1, 2/1 is 2, 3/2 is 1.5, 5/3 is 1.6 repeating, 8/5 is 1.6, and we continue and continue and continue to get these really long repeating fractions until we get something that stabilizes. So you can see that we go from 1, if you kind of draw it on a number line, where this is 1, and this is 2. So we go from here at 1 to 2, to then at 1.5 here in the middle, to then 1.66 to 1.6. And we just keep going back and forth around this point, right? If this is 1.5, we keep going around that point right here, where we have one that's a little bit bigger, then one that's a little bit smaller. And you can see that these increase and then decrease. So right here, we increase, then we decrease, and then we increase, decrease. 1.6 to 1.625 is another increase, and then we decrease, and then we increase, and then we decrease, and then we increase. So we're just kind of getting closer and closer to some number that's there in the middle. So if we were to look at these ratios and their decimal representations, whenever we had really large terms, right, the Fibonacci sequence keeps getting bigger. So if we just kept doing this, eventually all of the decimals, so the digits of the decimals steady out. And so they're eventually all going to look like this. So this is the number that we keep bouncing around, is 1.6180339. And again, it keeps going. So if you've ever seen calculus, this is really similar to the limit. So this process of steadying out as you get bigger and bigger is essentially what a limit is in calculus. So this is the golden ratio, these numbers that they steady out to. And so this has a lot of applications in geometry and art and architecture. And so this is one of the things that occurs naturally. So you can see it in the way that plants grow. You can just see it a lot, and it has it has a pictorial representation in it that's not in the book, but I'm pretty sure if you just Google golden ratio, I'm Googling it right now to see. Yeah, so if you just Google images, the golden ratio, you'll see this really nice spiral shape. That this spiral shape forms from looking at rectangles with different sizes that correspond to these ratios. And so this spiral shape is really naturally occurring in shells and different plants and different natural things. And so this is what made people first look at it. So yeah, these are the irrational numbers. So you can read about them a little bit more in the book on page 351, 352, and 353. But I just kind of wanted to highlight them. The book highlights them. If you ever, well, I'm assuming you're all going to have to take another math class, but I'm not quite sure if those other math classes use these numbers or not. But yeah, read about them, see what you think, and just be aware that they're there. But these are just some of them. There's actually infinitely many more irrational numbers, and a lot of them infinitely more irrational numbers, and a lot of them are useful in a lot of different things. So you can see that this number E, you wouldn't really expect that this sum of this sort would help us calculate interest, right? You wouldn't normally guess that, but it's true. And pi is used for just a bunch of different things. So yeah, you wouldn't guess that a lot of these numbers have a lot of applications to things, but they do, and they're really useful that way. So this is all I really wanted to say about these famous irrational numbers. So that's all for this section and this chapter and this course and this video.